name is Chanyoung PARK, and I'm going to be introducing you to reinforcement learning and the multi-arm bandit problem. Okay, so first off, what is reinforcement learning? It is one of the four types of machine learning, first being the supervised learning, which basically means the AI model has to get something right. This could be image recognition, see a picture of a cat and say it's a picture of a cat, or predict the stock price or something that has a correct answer. Unsupervised is something that doesn't have the answer. It's fed a lot of similar pictures, similar data, and it's told to make something similar. On the right is a person that does not exist from a website called thispersondoesnotexist.com. It's created by an AI model that was fed a lot of people's portrait photos and created one that it thought was similar. And you can actually just go to that site and infinitely generate people that don't exist. So this is used for like writing, AI writing stuff, AI creating images, music composition, all these more creative stuff. Okay, next is partially or semi-supervised learning. This is, in a way, more practical way of doing supervised learning because you need to give an answer for supervised learning. And when you're trying to make a good AI model, you need to feed a lot of data, like tens of thousands, hundreds of thousands, sometimes like millions of data. And it's when, say, we're trying to make a model that can recognize objects through image, it's really time consuming for the developers to label like 2 million photos saying that's a cat, that's a dog, that's a cat again. Or so instead what they do is just label a portion of it and make it work that way. It's less effective, but it still works and it's far more efficient. So that's the semi-supervised learning. And finally, the reinforcement learning, which we'll be doing today. This one is special because this doesn't have any training data. All it's given is environment, and your model has to sort of find its way through it. So this would be problems like playing Pac-Man, playing chess, playing games, or possibly driving. AlphaGo was made using reinforcement learning and supervised learning combined. And the objective of reinforcement learning is to have the highest reward possible. Reward would be some way of rewarding the model for doing the right thing. How it's calculated will be explained soon. So here's the basic structure of reinforcement learning. There are two main entities, agent and the environment. There might be multiple agents, there might be multiple environments, but in general, there's going to be two main entities. Agent is your artificial intelligence model. It's going to be what you're going to be developing. Environment is like, say, in chessboard, it's going to be chessboard. And it'll be modeled as Markov decision process. What is Markov decision process? Well, it's an entire topic on its own. So all you need to know is that the steps are going to be separated into state, action, reward, and next state. This makes little sense on its own. So here is a diagram. So agent is going to get the state here. And with the state, agent is going to decide what action it's going to do. The action is sent to the environment. The environment makes the change, gives the next change to interpreter, and interpreter calculates reward and passes on to the next state to agent. So for example, in a game of chess, you might start off with a normal chessboard settings and your agent might tell you to move the F pawn, say, which I think is a terrible move, but still does random things. So it does it, environment reflects that and makes the change on the board, sends the changed board to the interpreter, and the interpreter will say, hey, that's a terrible move, or that's a great move, and send the reward accordingly to the agent as well as the next state. And that will just repeat until the game either ends or you win, or whatever. Interpreter is kind of strange here, and as I said, this is basic structure. This may change as much as it possibly can. Interpreter just might be in that environment. So in, say, Pac-Man or most arcade games, points are already given to you. You don't need to separately calculate the reward. But in a chess game, there are points, but your objective is not to capture as many pieces as possible. It's to checkmate. So you're going to have to find some other way to reward the agent. Okay, so how are decisions made in agents? So there are two main categories of decision-making processes in reinforcement learning. First is the policy-based. This is basically a manual for the AI. AI, develops a manual. They go to the same state multiple times over the course of some time, and they just figure out which action is the best at each state. There's value-based, which means they're going to have some sort of function that predicts, has some way to calculate the expected reward for each state for an action, and they're going to choose the best one. They might sound pretty similar. They kind of are, but if like logically, but when we get to the equations, which will not in this presentation because it's pretty big, it gets quite different, and some methods are better in other cases. It's case by case sort of. But what we're more interested in is how are these things developed? How do we evaluate each choice? We explore just the way you would do in any sort of games, any sort of activities. Say you're playing a chess game. I'm using chess a lot because I don't know, chess seems to be good for this. Okay, so say if you're trying a game of chess, you've never played before, you're going to do random things. You move your pawn again, and lose miserably, possibly. And you're going to just do that multiple times until you start to kind of get the hang of it, how to get a checkmate, how to, not waste your pieces. And, eventually you'll get better at it. And this is going to be the same thing for the agent. It's going to do random things, and it's slowly going to learn. But so exploration is necessary, right? You can't just start making decisions when you don't know anything. But the problem is you can't explore forever. So for example, in a chess game or a Go game or any game that has a lot of possible actions, you can't try out every single state and every action and evaluate them. At some point, you have to say that's enough exploration. We have to just use our strategy from now on. And this is the problem of pretty much every reinforcement learning. You have to, at some point, just go with the exploitation instead of exploration. Okay, so one of the problems that you can, kind of feel this dilemma the best is the multi-arm bandit problem. So basically, you're in a casino, hopefully a legal one, and you have a row of slot machines with different probabilities of winning, different points. And you get to roll them a total n number of times. And you definitely want to make the most money out of it. You have to know, you have to try all the slots, see which one is the best, but you also have a limited number of rolls. So this is a classic problem of exploration vs exploitation, makes the optimization necessary. Okay, so here's the one I did from like, a year ago, which I revised yesterday night. Here's the basic functions. I'm not going to be explaining them. You can stop the video possibly and just look through them. It's not complicated too much. And here I set up the slot machines. You times these numbers by 10, and you have the average points you're going to get from each slot. You can see that this one's going to get 6.1, 3.5, 4.7, and this one is the highest one with 9.6 points average. So what you kind of want your model to do is find this slot and just use this over and over again. So first strategy I used was exploring by probability. That was not supposed to happen. Okay, exploring by probability. This is one of the most common and basic strategies used. This is called the epsilon greedy. By the chance of epsilon, it's going to do something completely random, disregarding every experience you've had. If it's, otherwise, it's going to do something that it thinks is the best. Be greedy with it. So in this case, I set the epsilon to 0.2, meaning 20% chance of doing something random. And I set the limit to 1,000 plays. It plays, and here is the average reward. You can see that it increases quite quickly, and then it's stable. This is pretty nice, but when you actually look at the numbers, you can see that the average ends up with around 8.3 or something, and we can see that the total amount of money we earned is $8,688. Python does some weird things, and they decided to round it up. No, like unrounded. I don't know how they did that. Okay, so this is okay. You know, $10,000 is probably the most you can get, and they got 8,600. But if we look at how many times the model tried each slot, we can actually see that they tried it a lot of times. Like they, 20 times for the first slot, 14, 30, 25. And here's the problem of exploration coming in. Some might think this is just enough for exploration. This is a point where we can confidently say that's the average, and you can see that they're actually really close. This is the predicted by the model, and this is the actual accuracy. They're often off by like 0.2, which is really accurate. But some may think they tried this too much. You can see that although they found the highest one is 9.61, the 8th slot, the average ends up being around 8,600 because epsilon, the probability of doing something random, is preventing them from making the best choice despite them knowing it. So I decided that let's try to lower the epsilon every time, do something that's logical as we get the sense of what's happening. So I decreased epsilon by 0.0005, which may sound like a little, but we're doing it 1,000 times. So epsilon is going to be completely gone in 200 runs. I run it again, around the same trend. We actually earned around $700 more in this case. That's quite the profit. And you can see that this time we only tried it like 3 times, except for the first one, which was 37 tries. Here is the problem again of exploitation. Yeah, this time is the problem of exploitation. Because we weren't exploring enough, we didn't get to actually evaluate the 8th one properly until we were lucky enough to actually check it again and realize, oh, this is far better. You can see in this graph that it just stays in around 6, the average, because it didn't get to realize that this is a far better option. So we were really lucky here, and we could have just ended up with like 6,000 if the exploration phase ended before they got to evaluate this further. You can see that they most only got like 2, 3, 4, 5 tries, which is, statistically speaking, probably not enough to decide whether something is good or bad in this case. Okay, so there are more strategies. I'm not going to go through all of them because there's a lot. You can just change the epsilon. You can change the number of tries. If you want to change the problem up a bit, you can say, let's just try every choice like 10 times and then decide which one's the best. There are many strategies to these, but what you should be taking away is that multi-arm bandit is a great problem to do these things. It's one of the most famous examples, and I would actually recommend just pausing the video at some points in the video, and try copying the code. Actually, you can just copy this thing and paste it. It's shared. Try different strategies out, and you'll get the sense of better sense of reinforcement learning and how they work. Okay, that is it for me, and thank you for listening, and have a good day.